In the previous class, we learned about how to implement the pipelining in the real RISC-V processor design. So actually we learned that, so the basic things we learned in the previous class is that, so now to implement the pipeline architecture, so we start from the single cycle processor design, and then based on the 5 steps of this single cycle processor design, we can insert pipeline registers, and actually these pipeline registers are D flip-flops. So actually we can insert D flip-flops between 2 neighbor steps. Okay, so in the previous class I mentioned that this single cycle processor design is composed of 5 steps. Okay, so you need to remember these 5 steps of the RISC-V processor. So instruction fetch, instruction decoding, execution, memory, and write back. And then in order to implement the pipeline architecture, we can just insert the pipeline register. That is the D flip-flop. So if we insert D flip-flops between neighbor steps of the single cycle process design, and the result, so what is the result of this instruction fetch staging? So the program count value and instruction. So result of the previous step is sampled by this D flip-flop. So sampled at the rising edge of the clock here. And then during this clock period, this sampled result of the previous stage is propagated to the next stage. So this ID stage can receive the result of the instruction fetch stage at the rising edge of this clock period. So that is the basic implementation of the pipeline architecture. Also, we learned in order to implement the correct pipeline design, then we need to meet the timing of the signals. Okay, so this is actually very important. If we just miss the correct timings of signals in the pipeline architecture, then this pipeline processor will generate incorrect result. So we cannot use that processor. So we need to beat the correct timing of each signal. So for example, for the write back stage, but if we remember that we can adjust the timing of each signal by seeing when this signal is required. So that means that, so if we just remember when this signal is required or consumed, I mean that the signal is used, then we can decide the correct timing of this required signal. Okay, and it's very simple actually. So the write register number here, write register number and write data is required, which stage is, so this write register number and write data are consumed at write back stage. So in order to meet the timing of this write register number and write data, we can delay this write register number and write data through the pipeline register. Okay, so I mentioned the delay. So if this signal go through this pipeline register, and it is mentioned that this signal is 1 clock delayed. Okay, so this is some signal, and then the signal is delayed by 1 clock. So we usually use this convention postfix, like interval D1. So that means that the signal is delayed by 1 clock period. Okay. So in order to meet the exact timing of this write data signal and then write register number, we can make this signal delayed by pipeline registers. That means the D flip-flop. So we can meet the timing of the required signal at write back stage. Also, control signal. It's very simple actually. So control signals are produced at instruction decoding stage. So that means that control unit is located in this instruction decoding stage. So actually these control signals are generated at instruction decoding ID stage. But when these control signals are consumed, it depends on the property of control signals. Okay, so and then also the basic basic idea is very simple. So as I explained, if a certain control signal is consumed, if a certain control signal is required at a certain stage of the pipeline architecture, then we can adjust the timing of this control signal by making the signals delayed by pipeline register. Okay. So for example, if a certain control signal is consumed at EX stage, then this signal is just go through this ID and EX stage pipeline register. So that means that this control signal is propagated to the EX stage, and then it is consumed at EX stage. And then if a certain control signal is consumed at memory stage, then this control signal go through this IDX stage and EX mem stage, like the data. Okay. And then these control signals are connected to the control port of the data path element in the memory stage. Okay. Actually, the basic idea is very simple. Okay. So, so we learned about we learned until this slide. So this is some completed pipeline architecture design. It's not completed, but it's the basic architecture of pipeline processor. And then at this time, so in today's class, we will learn about how to handle data hazard. Okay. So what is a data hazard? So what is hazard? So you need to remember that. The hazard means that it's the event that make clock period wasted, clock count is wasted. Okay, that is the definition of a hazard in the processor design. Then why data hazard happen? What's the reason of data hazard? It's data dependencies between two instructions. Okay, so actually in the previous class, we learned how to handle data hazards in the pipeline architecture. The first solution is data forwarding. And then the second solution is, so with the data forwarding, then we can deliver the data to the required data path element at some required timing. Okay, it's the data forwarding. And then what's the second solution? The second solution is pipeline store. So the load used data hazard, so we cannot avoid wasting one clock. Okay, because the result of load instruction is generated at the end of the memory stage, but if the very next instruction requires the result from the former load instruction, then when this next instruction is in the EX stage, the load instruction is in the memory stage, but the required data, that means the result from the load instruction is not generated yet. So next instructions cannot be performed by ALU because the operands for ALU is not ready. So in this case, we need to store pipelines of the processor. So that means that the next instructions cannot be performed in the EX stage. So the pipeline stalls, that is called the pipeline stalls. So the first solution is data forwarding, and then the second solution is a pipeline store. So in the pipeline design, we need to know how to implement these data forwarding and pipeline stores by data hazard. Okay. So actually, I believe the implementing the basic pipeline architecture is relatively simple. So I believe it's simple. Okay. But if we just consider some exceptional cases such as data hazard or control hazard, then controlling these hazards may be somewhat complex. Okay, it's not as simple. It's not as simple as the basic pipeline design. Okay, so please focus on today's class. So this is the example code of the that shows the data hazard between the sub instruction and following instructions. So in this example code, you can find that the result of sub is stored in X2, the register X2, and then the following instructions and for add SD requires the result from this former sub instruction. So, and receive the X2 here, or also requires the result from this sub instruction. And then this add instruction requires the two operands from this X2, and then SD also receive the data from register number X2. Okay, so if you see that this very special code, you can find that every following instruction requires result from this one sub instruction. Okay, so that means that this code will cause data hazards. So, but the good thing is that this instruction is not a load instruction. It's not load. So what does that mean? The result of this sub instruction is actually produced at the end of EX stage. And then also we learned that so this AND or add SD requires this data in X2 in EX stage. Okay. So actually this is because this instruction is not a load instruction, then we can forward the result of the sub instruction to the following instructions. So that means that we can avoid data hazard using data forwarding. Okay. So that means that this data in X2 can be forwarded to this AND instruction, forwarded to the OR instruction, or can be forwarded to X2 or X2. So let's see when this instruction is consumed by following instructions. So let's see the pipeline diagram. So if you see this pipeline diagram, then you can, I believe you can easily understand when the result of sub instruction is consumed. So when the result of sub instruction can be consumed by following instructions. So this is the sub instruction, and then as you know, the result of sub instruction will be written back at write back stage. Okay, here. And then it's the clock cycle number 5. But we already learned that because the result of sub instruction is generated by ALU. So here is an ALU. And due to the delay of the ALU, the result will be generated near the end of this clock cycle number 3. So sometime here. And then if you see this following AND instruction, so we know that the AND instruction requires data from this sub instruction, but you know the result of this sub instruction is generated at the end of the clock cycle number 3, and then this AND instruction requires operand at clock cycle number 4. So this is the future and the past. So data can be forwarded. So in this case, this data can be forwarded to the input of the ALU. Do you understand? So that means that actually the original path for this ALU comes from this pipeline register. So actually the output of this register file. But instead of this path, for this AND instruction, receive the data from the output of ALU. Okay, so we need to, so this is the data forwarding, and for this, in order to support this data forwarding, then we need to make a, what is required? So I believe everyone knows, oh, with the data forwarding, we can avoid data hazard. So the data can be forwarded, but what is required in the hardware? Port, yeah, port. So actually the port is already exist. Port already exists in the data path element. We need the path. So we need the forwarding path to this ALU. Okay. So we will learn about this forwarding path in this class. Okay. So that please remember that we require the path for this data forwarding. Okay. Path. And how about this OR instruction? So OR instruction also requires data from this sub instruction. And then actually the OR instruction requires data at clock cycle number 5. But this result is located in this memory write back pipeline register. Okay. So when this OR instruction requires data for this ALU operation, the result of sub instruction is not yet written back to the register file. Understand? So, but we already know that the result is generated at this time, and then so that means that the result is propagated to the write back stage. Okay, so we can find that the result already exists in the pipeline processor. So this result can be forwarded to this ALU. So this data forwarding can be also implemented using data forward path, but this path is different from this data forwarding path. Why? So this data forwarding is implemented using the result in EX memory pipeline register, and the data forwarding path for this data forwarding is you need to use the data in memory write back pipeline register. So we need the different data forwarding path for this data forwarding. Okay. And how about this add instruction? So if you see the timing of the sub instruction and the add instruction, then at clock cycle number 5, the result of the sub instruction is being written back to this register. Okay, and the add instruction is reading data from the register, this register file, and then with the same register number. So if we just see the register file here, then for the RS1, the register number is 2, and then for the RD, also the number is 2, and then the new data. So that is the result of sub is being written back to the register file. So what is this case? While this add instruction is reading data from the register file, I said while, and then at the same time, the required data is being written back to the register file. So actually, for this case, this result data should be delivered to the output port of the read data 1. Oops. Read data 1. So I mentioned that this data, which is being written back to the register file, should be forwarded to the data output of this register file. This is called the internal forwarding. So internal forwarding means that when a certain data is being returned back, and then if this data is required by this source register of the register file, then this data which is written back is forwarded to the output port of the register file. This is the internal forwarding. So in this course, we assume that the register file support the internal forwarding. So, and then if you see the lab assignment number 2, and then if you see the skeleton code of the register file, then you can find that you need to implement the internal forwarding. Okay. Then, but it will not be difficult because if you understand how the data can be forwarded to the output of the register file. Okay. So this data dependency can be solved by internal forwarding of this register file. How about this store instruction? It's actually just we don't need to consider about the data hazard for this store instruction. Why? The result of the sub instruction is already written back to the register file at clock cycle number 5, and then the store instruction reads operand from the register file at clock cycle 6. So when this data is requested by store instruction, the requested data already exists in the register file. So we don't need to consider data hazard for this case. So what can you know? If we just consider the data hazard, then we can know that. So we need to handle the data hazard for the very next instruction, and then data hazard for the next instruction, and then so we need to consider the data hazard for the next instruction. Okay, but we can solve the data hazard using data forwarding for this very next instruction with the data forwarding from EX memory pipeline register to the ALU. So this figure, this forwarding path. And then for this second next instruction, we can solve the data hazard using also the forwarding path from memory write back pipeline register to ALU, like this figure, this path. How about the third next instruction? We can solve data forwarding using internal forwarding in register file. Okay. And then for the first next instruction, we don't need to consider data forwarding because the required data already exists in register file. Okay. If we just understand the required timing and then where the data is forwarded from, then I believe you can easily understand how to implement the forwarding path in the pipeline processor. Okay. So this slide actually summarized what I said in the previous slide. So, and then in order to support the data forwarding, then first we need to define when the data forward is required. Okay, that means the condition for the data forward. So if you see this code, like here, if you see this example code, then we can easily know that we can easily figure out the conditions for data forwarding. What are the conditions for data forwarding? So this is the RD, destination register of this former instruction. If the destination register number of the former instruction is equal to the one of the source register number, where as 2, then we need to consider data forwarding. Right. So for this example, the ID of the sub instruction is equal to the RS1 of the end instruction. And then for this OR instruction, this ID of the sub instruction is equal to the RS2 of the OR instruction. So we need to check the register number for former ID, the destination register number of the former instruction, and the register number of the source registers of following instructions. Okay. So this slide explains this condition. And then if you see this pipeline architecture, then you can find that this is the ALU result. Then this ALU result is propagated to the next stage via this EX and MEM pipeline register. So actually, this is the result of this ALU, and this ALU can be used by next instruction. Okay, and then how about this path? So if you see this path, oops, you can find that the result of the ALU is also propagated to write back stage through the memory write back pipeline register. So we can find that result of ALU in this memory stage, also in the write back stage. So this result can be forwarded to the one of input of the ALU. Okay, this is the forwarding path. Also, in order to check the forwarding condition, so when this forwarded result is required, the forwarded result is required at EX stage. Okay, so the sub is here, and what's the next instruction? So end instruction. And is here, and this data will be delivered to the one of the input of this ALU. And then that means that RD, destination register number of the sub instruction, is here, and then where is the RS1 is here, RS2 is here. So actually this is also forwarded, propagate to this EX stage. So we need to check the RS1 and or RS2 of the end instruction. So in order to check the forwarding condition, so if we just focused on the data forwarding between sub and end, first, we know that the data, the required data, is forwarded from the EX mem.exe ALU result. So that is the this data, just that this EX the EX MEM pipeline register. So this data should be forwarded, and we need to check the RD of this sub instruction and or RS1 or RS2 of the end instruction. That's the very next instruction. So in the pipeline diagram, when the sub instruction is here in memory stage, that means that the result of sub instruction is also here. That means the RD of the sub instruction is also in the memory stage, where here. And then where is the RS1 and or RS2 of the end instruction? The end instruction is in the EX stage. So that means that in order to check the forwarding condition, we need to deliver this RS1, RS2 through the ID EX pipeline register. Okay. So these source register numbers are also forwarded to the pipeline register. So RS1 and RS2 of this end instruction is compared to the RD of the sub instruction. Okay, so this timing is very critical. But if you remember, so just remember that where is the sub instruction and then where is the end instruction? We need to check the data forwarding condition between this sub and end instruction. So sub is in the MEM stage and then end is in the EX stage. So we need to check the RS1 and RS2 of the end and then RD of the sub. So that means that we need to check the RD of the sub. What is the RD of the sub? This is this one. And then what is the RS1 and RS2 of the end? This is here. So this is propagate to this stage. So we need to compare the RS1 and RS2 of this pipeline register and then RD of this pipeline register. Understand? So in this slide you can find this condition. So you can find that EX MEM pipeline register and then register number RD. You need to check the equality of this RD with the ID EX pipeline register of RS1. ID and RS2. So that means this one and this one. Understand? How about the sub and OR instruction? So for this data forwarding from sub to OR instruction, we need to use the result, ALU result in memory, write back pipeline register. Why? In this case, the sub is here, and is here, and then this is OR, right? So OR instruction. So the result of the sub instruction. What is the result of the sub instruction? This one. This one should be forwarded to the one of the inputs of ALU. Okay. So sub is here. So in this example, we need to check the RD of this sub instruction and RS1 or RS2 of the OR instruction. Right. Where is the OR instruction? OR instruction is in the EX stage. Sub instruction is in the write back stage. So how to check the forwarding condition? RD of the sub instruction. Where is the RD of the sub instruction? This one. And then RS1 and RS2 of the OR instruction. Where is it? Here. So we need to check the equality of RS1, RS2 of this pipeline register and RD of this pipeline register. Do you understand what I said? So this is this condition represents the data forwarding from memory write back to the EX stage. Okay, so we just check the memory, the RD of the memory write back pipeline register with the RS1 of the ID EX stage. So this first condition is for data forwarding from EX memory pipeline register to ALU, and then this second condition is the data forwarding condition for forwarding from memory write back pipeline register to the input of ALU. I hope everyone can understand. So this is the basic condition for data forwarding, but we need to consider this destination register is valid. So that means, so I said we need to consider the destination register number is valid. So what is the case? Sometimes the store instruction, for this store instruction, this instruction does not have any destination register. But you know, so when the store instruction is decoded, RD may have some values, even though this RD is not valid. So this RD is also included in the, actually RD is included in the load instruction and R-type instruction of the RISC-V instructions. But for the store instruction, RD is actually the RD field of this load instruction, and then R-type instruction is the part of immediate value. So that means that even though the store instruction does not use RD, the destination register number, but even though the store instruction is executed, the RD is the, we define the some field of the instruction. RD may have some values. So if we just use this condition, even though the store instruction is executed, then RD may have some values. Then we need this RD is compared with the RS1. So in this case, we can apply the incorrect data forwarding. So in order to avoid this case, we need to check the leg write control signal. Do you understand what I said? Well, I can't find wait a second. So where is the RD? So if you see that this RISC-V instruction format, so this means the instructions of the RISC-V, then we can use the RD from inst from pin number 11 down to 7. So actually the RD is inst pin number 11 down to 7 for the I-type or I-type instruction, so load instruction. But for the store instruction here, the ID is filled with the immediate value. So that means that immediate value will have some values. So even though the store instruction does not use this RD, the RD is the part of the instruction, then this RD may be filled with some garbage value for the store instruction. Then what's the problem? We can compare this garbage value with the RS1 or RS2 of the following instruction to check the data forwarding. So in order to avoid this case, we need to check the leg write signal. So leg write signal becomes 1 if this destination register has the valid register number, right? So we need to check this leg write. Also, we need to check if the RD is 0 or not. Why? Add x0, x1, x2. So even though this add instruction stores its result to the x0, how about and then solve x2, 3, x0, x1. So in this case, do we need for the x1 plus x2 to x0? If we forward the result of the ALU to this x0, then what's the problem? It will generate the incorrect value. Why? In the RISC-V instruction set architecture manual, we define that the value of the x0 is always 0. So we cannot forward the result of x1 plus x2 to this x0 of the following instruction. x0 should be 0 always. We need to avoid this case also. Understand? So we need to check the destination register is 0 or not. So another condition is that the destination register of the former instruction should be non-zero. Okay. So and then let's define the forwarding path. So the ALU can receive each operand from the register file. So here, and from memory stage, that means here, and from write back stage, this one. So actually, this one. So this input of the ALU can receive the data from the register file. This is normal case, and then data from this path here. And then data from this path. Okay. Here. So that means this input port of ALU receives one of these three different results. So result from register file, and then one result from memory stage, or result from write back stage. So we need to select the input of the ALU from these three sources. That means we need multiplexer, right? So there are multiple inputs, and then we need to select from these multiple inputs. That means we need multiplexer. Then for this folding, you need to remember where you need to know the folding path from the memory and then write back. So this path is forwarded to the ALU, and then this result is also forwarded to the input of the ALU. So if this is A, and if this is B, and then this is the A, and then okay. This is B, this is A. Also, the result from memory or write back stage can be another input of the ALU. So this is also delivered to the page here and to here. Also, another input from the register file. So in order to build the folding path inside of the pipeline architecture, then we need to add the multiplexer in front of ALU. Okay, understand? Also, if we add a multiplexer, then we need the selection signals for this multiplexer. So this selection signal is generated by control unit called the folding unit. And then this selection signal for this multiplexer, and then this multiplexer is generated by this folding unit. So if we focus on this folding unit, what signals are required? So if you see the input of a folding unit here, 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 here. What is this input? It's the RS1, it's the RS2, but from the ID EX pipeline register. Okay. How about the ID? So ID from this EX memory pipeline register, and ID from memory write back pipeline register. So this folding path receive these signals. So what is missing? Mem write. Oh, no, reg write. The folding unit also need to receive reg write signals from the pipeline register. Okay. Okay, try to understand the folding path. This is very important. So, because if we build the incorrect folding path, then the processor will generate the incorrect result. Okay, so we need to build the correct folding path. But building a folding path is a little bit tricky compared to the building basic pipeline architecture. Okay. So this slide summarized the multiplexer selection signals here, and then the source of which source input is selected for this multiplexer, then what is the condition. Okay. But we need to also consider the very special case. it's called the double data hazard. So if you see this code, then you can find that. So there are 3 ads, and then the second ad receive the result from this ad, and then third ad receive the result from the second ad. It's simple. Then what's the problem? When you learn about the data forward, then the data, we need to consider the data forward from the first instruction to the second instruction. This data forward is the memory stage to the ALU. And then we also need to consider the data forwarding from the first instruction to the third instruction. That is the write back to the input of ALU. What's the problem? This example qualifies its condition and its condition. So which data should be forwarded? So for this third instruction can receive the data from the first instruction, this case, and then receive data from the second instruction, this case. Hold on. Receive the data from the first instruction, this case, and then receive from the second instruction, this case. What is the correct forwarding path? A or B? B, right. We need to activate only this forwarding path. That means the memory to ALU. Why? Because this is the latest value for X1. And then this is the following instruction of this third instruction need to receive the latest value. This is the old value. Okay, so actually this old value is overwritten by the result of the second add instruction. So we need to read the third instruction receive the result from this second add instruction. We need to also consider this case. Okay, so what should we consider? So if the both forward conditions are true, then we need to select the memory to ALU data forwarding. So I said both forwarding conditions are true. We need to select only this data forwarding. So this condition should be included in the forwarding meaning. Okay. So I believe this is a little bit tricky for those. A little bit tricky. So it's because there are lots of conditions. So we need to consider some exceptional cases to generate the forwarding condition to detect the forwarding conditions. Okay. So there are many exceptional cases. But in order to generate the correct forwarding selection signals, then we need to consider these corner cases. That's why the pipeline design is more difficult than the single cycle processor design. It's a little bit tricky. Okay. So this slide also considers these corner cases. Okay. So for the memory hazard, that means that if we just consider the data forwarding from write back to the input of the ALU, then we need to consider leg write signal, and then this register number. And then we need to also consider the memory to ALU data forwarding condition is true. So if this condition is true, we need to disable the write back to the ALU data forwarding. Okay. So we need to check this condition, and then if the RD is equal to RS1, this is the basic condition, then forward A becomes the 0, 1. What is the 0, 1? This is this one. Memory write back to the ALU. So we need to also consider this double data hazard. So there are many exceptional cases when for this data forwarding, or actually in the modern processors also, modern processors are more complex. So but actually the five-stage pipeline architecture is very simple, but if we just consider the data forwarding cases for this 5-stage pipeline architecture, data forwarding conditions are also a little bit tricky. So this slide shows the pipeline process architecture which have data forwarding unit. So you can find the data forwarding path from the here to where is the here, and then data forwarding from here to here. A is here, yeah, A is here, and then the forwarding unit is located at EX stage here, and then forwarding unit received the RS1 and RS2 register number from this ID EX pipeline register, and RD from EX memory, and then memory write back pipeline registers. Okay. And then the next topic is the hazard detection. So actually for these data hazard cases, we can solve the data hazard between this alt type to another alt type instruction with the data forwarding. So even though the data forwarding is a little bit tricky, but if we can implement the correct data forwarding path in the pipeline architecture, then we can avoid the data hazard. That means the waste of clock cycles. But how about the load use data hazard? So that means that the former instruction is the load instruction, and then the following instruction use the result of the load instruction, like add x2, x1, x1. So the result of load instruction should be delivered to the add instruction. But we know that this cannot be solved by data hazard. Data forwarding, sorry. This case cannot be solved by data forwarding. So in this case, the add instruction need to be stopped and then wait until the result of the load instruction is generated. Okay, so I said the add instruction need to be stopped. So this stop of this add instruction is called the pipeline stall. Okay. So in the previous class, we learned how to store the following instructions. Okay. So here, so in this example, this following sub instruction receive the data from the load instruction, but the sub instruction cannot be executed because the data is not ready at this clock cycle 4. So actually, this figure shows that the sub instruction is fetched here, but actual design sub instruction is fetched at clock cycle number 2, and then sub instruction is in the idle stage at clock cycle number 3, and this sub instruction is stored at clock cycle number 3 because the sub instruction requires data from at the EX stage at clock cycle number 5. Okay, so this pipeline store should be implemented for load use hazard. Okay, so this case. So this load is here, and then the very next end instruction receive data from load instruction. And then we know the data of this, the result of this load instruction is generated at the end of the clock cycle number 4. And then, so in order to use this result, the EX stage of end instruction should be at clock cycle number 5 here. But if the add instruction is, actually the add instruction is fetched at clock cycle number 2 here, and then it is decoded at clock cycle number 3. We need to decode the instruction because after the decoding step, we can know the source register number of this corresponding instruction. So, and the end instruction is decoded at clock cycle number 3, but end instruction cannot perform EX step at clock cycle number 4 because the data is not generated yet. So the pipeline stores. That means for one clock period, end instruction remains in ID stage. And how about then what happened to the EX stage? EX stage becomes the invalid instruction. This invalid instruction is called NOP. NOP or no OP. So NOP means that it's the no operation. Okay. So instead of propagating this end instruction, no operation, invalid instruction is generated and fills the EX stage here. And then after one clock, this end instruction can be propagated to the EX stage. This is the pipeline store for load use hazard. So, which operation is required for load use hazard? We need pipeline store. So that means first, instruction in ID should be stored. And then, because this instruction is stored in ID stage, there can be another instruction in instruction fetch stage, right? in instruction fetch stage also stored. So there are two instructions. There is one instruction in ID stage, and then another instruction is in instruction fetch stage, right? And then these two instructions need to be stored in the pipelines. But another instruction, another operation is that no operation or bubble need to fill EX stage. So these are required operation for pipeline stores by load use data hazard. So this operation should be also implemented. So how can you implement? So we need to first we need to detect the load use data hazard. What is the detection condition? It's simple. The formal instruction is load instruction, and then the destination, that means the RD of load instruction is equal to RS1 or RS2 of the load following instruction. That means the very next instruction. And that's it. So you now check that this condition, then, and then also you need to remember that the following instruction need to stay in ID stage. So that means this load use data hazard should be detected when the following instruction is in the ID stage, which means hazard detection unit locates in ID stage. Okay, it is required in ID stage. So hazard detection unit is in ID stage. Okay, so we need to check this condition. So mem read becomes 1 for load instructions. So we need to check the mem read. So load instruction is in the EX stage, and then following instruction is in the ID stage. So we need to check the load instruction in EX stage. So that's the mem read. Mem read becomes 1 for the load instruction. And check the RD of load instruction and RS1 or RS2 of following instruction. So we need to check the RD of this IDEX, and then RS1 and RS2 of the instructions in ID stage. Okay, so this is the hazard detection. So hazard, this is the condition for load use hazard detection. Okay. So I plan to complete this pipeline store also in this class, but I think I need to stop here. So I stop here. Then I will continue the pipeline stores in the next class. So please remember that. So this is a little bit tricky topic in the pipeline architecture design, because data forwarding requires some corner cases for, or some exceptional cases for this data forwarding. Also, this data hazard detection, then you need to understand how to store pipelines. Okay. So if you cannot understand, so please review what you learned in the today's class. Okay. Okay, I'll stop here. Do you have any questions? You can ask question after the class. Okay. So thank you for your attention and then see you in the next class. 네, 모금 답안은 뭐 따로 업로드 되진 않습니다. 스토어, 파이프라인 스토어하고 노프 오퍼레이션은 아까 여기서 이제 설명을 했듯이 그러니까 인스트럭션이 어떤 스테이지에 머무르는 것을 우리는 파이프라인 스토어라고 부릅니다. 그러니까 원래는 파이프라인 아키텍처에서는 에브리 클락마다 인스트럭션이 다음 단계, 다음 스테이지로 이게 프로파게이션이 돼야 되잖아요. 근데 그거를 프로파게이션 시키지 않고 딱 멈추는 거를 우리가 이제 파이프라인 스토어라고 이제 이야기를 하고 있고요. 근데 이제 문제는 이 같은 경우에는 그냥 파이프라인 스토리라는 거는 그냥 인스트럭션이 다음 단계로 안 넘어가고 그냥 멈춘다는 걸 얘기를 해요. 근데 이제 이 같은 경우에는 여기에서 이제 end 인스트럭션은 멈춰야 되지만 그러니까 파이프라인에 딱 멈춰 있어야 되지만 로드 인스트럭션은 계속 진행을 해야지 그 데이터를 이제 얻어올 거 아니에요. 데이터가 생성이 되겠죠. 그렇기 때문에 로드 인스트럭션은 계속 진행을 해야 됩니다. 문제는 이 EX 스테이지에 어떤 인스트럭션이 아무것도 없는 거죠. 인스트럭션이 없으니까는 그냥 nope이라고 이제 no instruction 이렇게 얘기를 할 수 있겠고요. 그러니까 nope instruction이라는 거는 이 파이프라인 스테이지가 아무것도 하지 않게 만드는 그런 인스트럭션을 이제 말을 합니다. 그러니까 스토리랑 노브는 약간 다른 개념이라고 이제 생각을 해야죠. 스토리는 그냥 전체 그러니까 파이프라인이 멈추는 거. 노브는 어떤 스테이지가 아무런 동작도 하지 않게 만드는 거. 그거를 이제 이야기를 하는 겁니다. 그래서 제가 좀 이게 필요한 오퍼레이션을 세 개로 나눈 것도 우리가 이제 스토어하고 이제 노브의 개념은 약간 달라서 여기서는 id랑 인스트럭션 디코딩이랑 인스트럭션 배치 스테이지에 있는 인스트럭션들은 스토어를 돼야 되는 거고요. 파이프라인에. 그 다음에 EX 스테이지 같은 경우에는 아무런 그 오퍼레이션도 하면 안 되기 때문에 높이 들어가야 됩니다. 네. 뭐 질문 없으면은 뭐 다른 그 리뷰하면서 나 복습하면서 질문 생기면은 그 피아자에 올려주세요. 이게 여기부터 그러니까는 파이프라인의 기본 개념은 그렇게 어렵진 않은데 여기부터 좀 어려운 그게 시작이 돼요. 타이밍도 막 맞춰야 되고 코너 케이스도 우리가 고려를 해야 되고 그렇기 때문에 이때부터 조금 어려운 부분이 시작이 됩니다. 그렇지만은 잘 공부해서 이해를 할 수 있도록 노력하면 좋겠습니다. 네, 수고 많으셨습니다.